Washington watches in horror as Iranian missiles grow deadlier, raising fresh fears over America's ability to respond. Could Iran's new missile warfare strategy outsmart America's arsenal as Tehran develops increasingly advanced ways to strike? Did U.S. AI systems fail against Iran once again, as the IRGC claims to reveal how it battered American war systems? The U.S. remains on its toes amid the Hormuz stalemate as Mojtaba's missile forces reportedly undergo a major upgrade. Iran continues to ramp up and evolve its missile systems amid the ongoing stalemate with Washington and rising tensions. IRGC spokesman Hossein Mohibi claimed Iranian missiles can now change trajectory mid-flight, making them harder to intercept. The missiles reportedly use advanced guidance and maneuvering capabilities to bypass enemy air defense systems, according to the IRGC. Mohibi also claimed Iran used missiles and drones to disrupt parts of the U.S. power network during the conflict. Iran reportedly targeted systems behind the enemy's decision-making process, rather than focusing only on physical military sites, according to Press TV. The IRGC said, and I quote, "Iranian missiles are no longer simply launched from one point and land at another. They have guidance and maneuvering capabilities. And some can change their trajectory during flight to bypass enemy air defense systems." When a data processing system is targeted, it is not simply a building that is destroyed. Part of the enemy's decision-making capability is being targeted. Likewise, when an air defense system is destroyed, it is not merely a missile or piece of equipment that is lost. Part of the enemy's air defense network is damaged. End quote. Iran also mocked America's reliance on high-end technology, claiming several advanced systems were ultimately intercepted or neutralized by the IRGC. Mohibi claimed the U.S. deployed AI, satellites, drones, radars and sensors throughout the war to identify and track Iranian targets. Iran further claimed America's technological network was used to identify targets, assess battlefield damage and track personnel during operations. The IRGC claimed that even this advanced technology ultimately failed to overcome Iran's resilience and ability to continue fighting. The IRGC said, and I quote, "Alongside these systems, technologies were used to identify targets, assess damage and track human resources. In fact, artificial intelligence was the coordinating element of a major part of this technological network. AI analyzed targets based on data received from various sources, but it could not monitor the institutional and ideological power of the Islamic Republic of Iran." Recently, Iran's deadly Qadr-F missile came back into focus amid escalating tensions with both the US and Europe. One of the most dangerous systems is the Qadr-F, described as Iran's longest-range missile derived from the Shahab-3 family. With an estimated range of at least 2,000 kilometers, the Qadr-F can reportedly strike targets far beyond Iran's borders. The missile has already been deployed during Iran's retaliatory strikes, demonstrating its potential role in Tehran's long-range arsenal. The Qadr-F is now reportedly emerging as a serious challenge to U.S. systems such as THAAD and Israel's Arrow missile defense network. Iran's Qadr-F. Key features are: the Qadr-F is a medium-range ballistic missile designed for long-range precision strikes and strategic deterrence. The missile is produced by Iran's Ministry of Defense as part of Tehran's expanding ballistic missile program. The Qadr-F is deployed from a mobile launcher, allowing the system to be relocated before launch. It uses a two-stage solid-fuel propulsion system designed to provide rapid launch capability and extended range. With an estimated range of around 1,950 kilometers, the missile can reportedly threaten targets far beyond Iran's immediate neighborhood. The Qadr-F measures approximately 16.6 meters in length, reflecting its substantial ballistic missile design. The Qadr-F is reportedly capable of reaching speeds of up to Mach 9, making it an extremely fast ballistic missile in its class. Its reported diameter stands at around 1.38 meters, giving the missile considerable internal volume for fuel and payload. The missile has an estimated launch weight of roughly 17,500 kilograms, making it a significant long-range weapon system. It can reportedly carry a warhead weighing around 750 kilograms, providing substantial destructive potential against strategic targets. The Qadr-F serves as a long-range strike and deterrence weapon, strengthening Iran's ability to threaten targets across a wider regional battle space. With its reported 2,000-kilometer reach, the Iranian ballistic missile could potentially place parts of Europe within its strike envelope. The Qadr-F gains even greater significance as tensions between Iran and several European nations continue to rise. This comes as Iran continues upgrading its deadly missile arsenal with new capabilities and features designed to expand its battlefield effectiveness. New images reportedly show a damaged Qadr-F re-entry vehicle fitted with a multi-element CRPA antenna array, suggesting that the missile may have carried a protected satellite navigation system inside its warhead section. According to technical assessments, the presence of a CRPA system indicates that Iran is advancing the guidance architecture of its ballistic missiles by adding greater resistance against jamming and navigation signal spoofing. Iran could potentially add more antenna elements in future designs to improve the system's ability to identify hostile interference and suppress several jamming sources at the same time. However, even a high-quality GNSS receiver alone cannot guarantee reliable guidance throughout a ballistic missile's flight, particularly when the vehicle is moving at extreme speed or operating under intense electronic attack. That is why high-performance inertial navigation systems remain essential, allowing the missile to continue calculating its position and trajectory even when satellite navigation signals become weak, distorted, or unavailable. Advanced gyroscopes and accelerometers continuously measure the missile's movement, rotation, and acceleration, enabling the INS to provide critical navigation data throughout the flight. GNSS and INS can work together in a complementary architecture, with satellite signals correcting accumulated inertial errors while the INS maintains guidance during brief interruptions or periods of jamming. Advanced algorithms and onboard computing can further improve guidance by filtering corrupted signals, combining data from multiple sensors, and constantly updating the missile's estimated position and flight path. The presence of GNSS equipment on an IRGC missile is therefore significant, but it does not reveal the full capability of the weapon because the receiver's performance depends heavily on its software, signal processing, and integration with the INS. The missile's inertial navigation system is a crucial part of the analysis, because understanding its sensors and processing architecture is essential to assessing how Iran's guidance technology is evolving beyond basic satellite navigation.
Upgrade your news experience with the all-new HT app. Download now.